Hello friends, this is the second tutorial on the energy equations. So already we have derived the energy equation. So if you have not see my last tutorial on the energy equation, you should go to the link and you should watch that tutorial where I have derived that how the energy equations can be written in the terms of the enthalpy and the internal energy. And here I am going to show you the perspective of the OpenFOAM. So how this energy equation has been coded inside the OpenFOAM, that aspects we are going to cover in this tutorial. Okay, so if you remember that, then in terms of the enthalpy we have derived these equations, okay, and in terms of the internal energy we have derived such equations. Okay, and how this derivation, we have started from the total energy and we started with the principle of the conservation law of energy. So the energy cannot be created or cannot be destroyed, it only transferred one form of energy into the another form. That is the basic principle of the derivation of the total energy equations inside the OpenFOAM, and from that concept we have derived these two equations in terms of the enthalpy and in terms of the internal energy. Okay, now we are going to see that how these two equations has been coded inside the OpenFOAM so that we can correlate with the different terms in the OpenFOAM. Okay, so these are the two equations. The first equation is the enthalpy and second equation in terms of the internal energy. Okay, now if we see and if we compare these two equations, okay, so first one equation is the in terms of the enthalpy and the last one is the in terms of the internal energy. So if we correlate the different terms of these two equations, so you can see that these terms are the similar terms. Okay, this first term, that is a transient term, that is a similar term. This is the second term, that is a divergence term, this is also the similar terms, and this is something that is the different in both equations. So here it is a del p upon del t, and this terms is the del dot v into p. Okay, and this is also a similar term. I am saying that a similar term, not I am saying that equivalent. This is just a similar term. So if we find the correlations, so we can see that here only the terms that is difference is the enthalpy, and here it is the internal energy, and this one is the kinetic energy, that is same in both of the equations. Similarly here we can see that this is the enthalpy term and this is the internal energy and this is the kinetic energy. So only the difference is that the H and E. Here that is the different terms that we need to treat in the different manner. Okay, so these two things we need to treat in the difference here, different manner, and this is also some kind of a similar term. So only the difference we saw here, that is the enthalpy and that is the internal energy. Okay, so if you want to make this equation as a user friendly, so we are going to ask user that whether you want to solve this equation in terms of the enthalpy or in terms of the internal energy. So we are going to first ask with the user that whether you want to solve in terms of the enthalpy or in terms of the internal energy, and then when the user specify that whether he or she wants to solve in terms of the enthalpy or internal energy, so based on that choice we are going to solve either this equation or this equations. Okay, so this should be keep in the mind while going to code these equations. This is the basic idea behind this coding these two equations. Okay, so only the difference that we are going to focus, and this term should be treated in the different manner. Okay, so what I am saying, let's go to the coding and then you can understand. So this is the coding here. You can see here that this two equation is coded, and I am taking the simple server, that is a Thermophysical. Okay, so this is the location that when you go to the foam app folder, and inside this foam app you will have folder of the solvers, and after that you will go to the heat transfer folder, and there is a solver known as a Thermophysical. Okay, so this code I have taken from the Thermophysical. Okay, so first let's understand it how the user is going to specify that whether he wants to solve the enthalpy or internal energy. So here you can see that this is where it is going to ask for that whether the user wants to solve for the enthalpy or internal energy. Okay, so you can see that we are creating a volume scalar field and we are storing whatever the specification is given in terms of the He. Okay, so He is another variable. So if this thermo.He, the output will be internal energy, then this He will be internal energy. And if this thermo.He output will be enthalpy, then this He will be enthalpy terms. Okay, so that is what it is going to specify. Now let me go to the OpenFOAM this solver folder and let me show that how this thermo is declared in the create field.h. So let's directly go to the Ubuntu terminal, and here if you go to the application folder, there is a folder of the solvers, and inside solvers there are different solvers has been given here, and we are just going to focus on the heat transfer solver. And here different kind of heat transfer solvers you can see here that, but I am going to just focus on the ThermoFOAM, which is the simplest solver related to the energy equations. Okay, so here you can see that there you can find the energy equations, and that is what I am showing you on the screen. So that is these terms we are explaining that how this compiler deciding that whether we need to solve for the enthalpy or whether we need to solve for the internal energy. Okay, so that is where the compiler is going to decide. And now what is a thermo? That is something related to the create fields.h. So when we go to the create fields.h, so you can see here that we are first creating the thermophysical model. Okay, so it is going to create the thermophysical model or thermophysical properties read from the this variable, that is the thermo. Okay, so first we are creating one class for every mesh. Okay, by passing the argument of the mesh, and this p thermo is variable, and then this variable is being referenced to the another variable, that is the thermo, and where now this thermo is going to ask for that whether we are going to solve for the enthalpy or internal energy using this validate command. Okay, so if it is validate this executable argument executable command equal to the enthalpy, then it is going to solve for the enthalpy, and if it is equal to internal energy, then it is going to solve for the internal energy. So that is where the solver or compiler decide that whether we need to solve for the internal or whether we need to solve for the enthalpy. Now this different terms we are going to understand in more details in the upcoming tutorials when we are going to focus on the thermophysical properties. That folder, that thermophysical properties folder is presented in the different test cases. When we are going to focus on those aspects, then we are going to understand these different lines. Okay, so here you can see that how we are defining the kinetic energy. Okay, so that K in energy equations, that is being calculated using the velocity only. Okay, so we are calculating this kinetic energy, and then we are solving this terms here. Okay, that is the ddt rho k and divergence of phi k. Okay, so this things we are solving. Okay, so here I think you have understand that how this compiler know that whether we want to solve for the E or P. So once it is clear that this H is either equal to E or equal to H, when it is clear now this equation is going to be solved accordingly. Okay, so let's see on the slides that what are the different terms in the equations here. So I think this is clear to you that how this compiler is taking care of that whether we want to solve for the enthalpy or internal energy. Now if you go to the next term, so that is terms, that is the transient term. So in transient term you can see here that first term is related to the either enthalpy or internal energy. So once it is clear that H equal to either E or H, so this terms is related to the enthalpy or the internal energy, and then these two terms, that is when we combine these two terms, that is the this del upon del T rho H plus K or del upon del T rho E plus K. So these terms you can see here that these two terms is related to the transient term, and now after that there is a divergence term. So this is also it is clear that once you find out that the H equal to either E or enthalpy, so this terms now you can correlate with this these terms that you can see on the left side and the right side also. And this is something where we are going to use the if and else. Okay, so remember that it is going to first check that whether he dot name equal to E. So when this is line is true, that he dot name is equal to E is true, then it will going to directly solve for this terms. Okay, so that is, you can see here that when we are checking that whether it is related to internal energy, then it will solve for the del dot V into P. Okay, so if this command line, this is the argument that it is checking here, whether this is he dot name equal to the internal energy. So if this is true, then it is going to solve for the this divergence of U into P. And if it is not true, okay, so that is why this question mark is written here. Okay, so this is one kind of a if else statement you are seeing here, that if this is true, then it is going to solve for this, otherwise it is going to solve for the minus del P upon del T. Okay, so you can see here that in case of enthalpy energy, we are solving for the minus del P upon del T, but in case of the internal energy, it is solved for the divergence of U into P. Now this del dot Q, that is also related to the heat transfer. So this H equal to either E or P based on whatever definition you are given here, and that will take as the Laplacian of, and alpha effective, that I have told you that it is the combination of the thermal diffusivity due to the turbulence and due to the laminar, and this alpha effective will be calculated, and after this terms will be calculated here. Okay, and after that the different other heat transfer resources, like if there is a radiation is present, or there is another kind of resources of the heat transfer or heat generation is present, so these terms are treated here. Okay, so this radiation will be taken care of the radiation model, and if you are providing some other source, heat source or heat sinks, then FE options, that is kind of the utilities of the OpenFOAM that you can use to create another kind of source here. Okay, so this is the equations that you can see here, that okay, I think this terms and this terms, and this is the heat conduction terms and radiation and every other heat sources. Now it is clear to you, and if there is a relaxation factor, so relaxation will be given, and this FE constraint will be provided here, and finally the energy equation will be solved. Okay, now let's see that this alpha effective terms, how it is being coded in the OpenFOAM. If I open the energy equations, so in energy equation, this is the variable that is related to thermodynamic diffusivity. Okay, now where the definition of alpha effective is written, so for that purpose we have to go to this folder, that is set alpha effective.h. Okay, so when I open this folder, set alpha effective.h, so you can see here that first we are creating a variable, temporarily variable, which is kind of the value scalar field. Okay, so this variable creating, that is T alpha effective, that is temporarily variable. Okay, now we are reading the turbulence properties. So if already some turbulence property is given in the constant folder, so this is going to read that dictionary from that file. Okay, now here you can see that there is one if else statement. Okay, so what it is doing, so first we are checking that whether some dictionary is present or not. So if there is turbulence properties kind of folder is present, then it will try to calculate using the turbulence model, and then whatever the value we will get, that is alpha effective, that is going to store into the T alpha effective variable. And suppose some turbulence model properties is not present into the folder, then it will automatically going to assign a value 0. Okay, so this is why if suppose in some folder you are not specifying that there is some turbulence model. Okay, turbulence model can be laminar, So that we are just reading the header file. So sometimes in the header files of the turbulence properties folder, you specify that you don't want to solve for the turbulence, you just want to solve for the laminar. So if there is turbulence properties kind of folder is present in the constant folder, then this loop is going to be solved, otherwise this loop is going to be solved. Okay, so if you are not have any kind of folder that is the turbulence properties, so automatically this alpha effective value will be 0. Otherwise we are going to use the properties that is assigned in the turbulence folder. Okay, now what are the different this folder that is going to be read, that we can see in the SRC folder. You can just go to the SRC folder, and here there is a turbulence model, and inside the turbulence model, inside the compressible, you may have this thermal diffusivity definition, and you can just explore this .h and .c folder, and here you can see that this alpha effective function is defined here, and similarly you can go through the .c folder and you can find the different constructor selectors, and similarly you can find the member functions. Okay, so this is how this alpha effective is being defined. This video is too much longer, so I have just explained that how this energy equation has been defined in OpenFOAM, and how this alpha effective is calculated in OpenFOAM, and how this can be switched between the entropy, this can be switched into the internal energy and enthalpy. So these aspects we have covered in this tutorial. So since time is already longer, so I am just limited to this point, and maybe in the next tutorial I am going to start with the thermophysical model definition in the OpenFOAM. So I hope you like this tutorial, and you should subscribe my YouTube channels, and maybe you can share the links of this YouTube channel to your friends. Okay, so thank you to all of you for watching with this video.